So the first story that actually, and the only story, because I'm going to spend all my time talking about this, is you might have heard in the news from last week about the announcement from NASA of people were calling it the second Earth, or Earth 2.0, or Earth's cousin. And so I'm going to talk about this discovery from the Kepler space mission. And this is an artist's depiction of what this world might look like. Nobody really knows exactly, and even whether it's a rocky world, there's still some uncertainty to it because the observations don't really allow us um, to figure out that much detail. But what we know is that this is a world that's about 60% larger than the Earth, so it's pretty close in size to the Earth. The solar system is about 1,400 light years away, so it's pretty far. But I mean, it's far for us, but it's pretty close by relative to the rest of the galaxy. And what's really exciting is that the star that it orbits is very similar to our sun. So it's a G-type star. It's only about 1.5 billion years older than our sun, meaning the solar system is about 6 billion years old. And this particular planet, which is the only planet that's known in this particular solar system, there might be other planets, but right now we haven't discovered any evidence for them. But it orbits in what's known as the habitable zone of the solar system. So it's neither too far nor too close for liquid water to exist on its surface if it happens to have a solid rocky surface. And so this is the closest solar system outside elsewhere in our galaxy that we found that is similar to our solar system in the sense of having an Earth-like world orbiting in in its habitable zone, or the Goldilocks zone, neither too hot nor too cold. And so I want to get into the details of how this discovery was made, the Kepler space mission, which we've talked about quite a bit in past 60 Minutes in Space presentations, but we'll go into the details of that, and then talk about some of the implications and what it all means. So the Kepler space mission is a mission that was launched in 2009, so it hasn't been up in space for very long, but its whole goal is to look for other solar systems and to even give us a sort of an idea of what the statistics of planets around other stars are, and also to find solar systems that are like ours, meaning trying to find Earth-like worlds or Earth-sized worlds orbiting in the habitable zones of sun-like stars. And you can sort of see that, well, obviously this is an artist's depiction, but what we're seeing is a star passing in front of, or a planet passing in front of a parent star. That's that black dot, and that gives you an idea of what Kepler is trying to do. So what Kepler does is it has a huge sensor, or a set of sensors, 42 of these large sensors, and the number of pixels is just shy of 100 million. So if you think about how many pixels are on your camera or in your phone, this is a lot more than what you typically have access to. And the idea for having such a big sensor is that they want to point it at a particular direction in the sky. So this is the Milky Way galaxy. So if you were to go out to a place far from city lights, you might actually be able to see this faint haze, which represents the disk of our Milky Way galaxy. Our galaxy has a couple 100 billion stars, and Kepler is pointed just at one particular position. So it does, for its primary mission, it didn't move around, although it's actually currently in a phase called K2, where it is looking in different parts of the sky. But for its primary mission, it looked in a patch just off of the arm of Cygnus the Swan. So if you know where Cygnus is in the sky, you could actually find it tonight after this event is over. But you can see the footprint of those detectors, and it's a pretty large footprint on the sky. If I remember right, this is probably about both your fists if you extended them out and imagine how big they would be. It's about 115 square degrees, so it's much larger, many times larger than the full moon. And the idea is that it stares at all these stars, hoping to find a transit event. So what's happening is that if this extrasolar planetary system is just aligned with us so that the planets, as they orbit, pass directly in front of the star, if you can measure the starlight very accurately, you can actually see a dip in the starlight when the planet passes by in front of the star. Now, you can imagine this is a very difficult thing to do. First of all, the planets have to line up so that the orbits have them passing directly in front of the star. And so this won't find solar systems where the orbits are tilted relative to us. And you could have a small tilt, but the tilt has to be very small. And then you can imagine that the drop in starlight is very small. So for our sun, if an alien astronomer was using the same sort of telescope and looking at our sun, and if they were to record Jupiter passing in front of the star, so let's see if we can redo this animation, the drop in starlight is about 1%. Whereas if they were trying to find an Earth, meaning our Earth, passing in front of our sun, it's on the order of about 80 parts in a million. So that's how much your sensors have to be able to detect, and the Kepler sensors are able to detect down to about 20 parts in a million. So it is able to find Earth-like planets, and of course, you can't guarantee that you'll actually see this transit occurring unless you just stare for a really long time. And so that's what Kepler does. They basically take observations every half hour, and so they're sending back these images of that particular patch in the sky, and they have to sift through all that data to look for these changes in the star's brightness. And so this can take a really long time to do, especially if you're looking for an Earth-like planet around a Sun-like star. You would expect a transit to take place once, roughly about a year. So in order to confirm this, you have to have multiple years of observations. And just to show you how accurate the detector is, this is an observation from a second phase of Kepler's mission. And what we're looking at is the planet Neptune with its moon Triton in orbit around it. And you actually see it go backwards because of retrograde motion as the Earth orbits around the Sun, or Kepler orbits around the Sun. It's in an orbit very close to the Earth's. So what happens is Neptune appears to go backwards. So let's see if we can watch it again. But what I want you to notice is not just Neptune, which is pretty cool, but look at these other stars. These are background stars, and they don't change at all. So the reason why Kepler is in space and doing what it's doing is because stars don't twinkle in space. There's no intervening atmosphere, and everything else in this image looks rock solid. So if there was a very small shift in brightness of a background star, you can imagine that with sensors this accurate, Kepler would be able to find it. So here are locations of candidates for planets that Kepler had detected as of 2.5 years ago. So this is a while back, and I'm trying to remember how many. This is probably on the order of about 2,500 objects, and right now the of planetary candidates is over 4,600. But you can see that there are a bunch of, they've not only have identified potential planets, but they range in different sizes. So from Earth size to Neptune and Jupiter or larger. But there's also this so-called super Earth category which is between 1.25 to 2 times the diameter of the Earth. And what's really interesting is that this particular category of super-Earths, so here we have showing the Earth, Neptune, Jupiter, and a much larger super Jupiter sized planets. And this histogram shows the number of planets in each of these categories that were known in early 2013. But what's really interesting is that the planets between Earth and Neptune are the most common that have been found so far as of a couple of years ago. And it includes this category of planets that is unknown in our solar system. So we don't have any planets in between Earth and Neptune size. Everything is either smaller than the Earth or Neptune size and larger. And Uranus is about the size of Neptune. So we basically we've discovered something really interesting, is that our solar system is missing this particular category of planet. Now, there have been a number of different techniques that have been devised to look for planets, and this particular paper shows all the planets that have been found using these other techniques. Well, Kepler is a transit technique, meaning it's looking for the shadow of a planet passing in front of its star. But these are transits that were found by telescopes on the ground. But the most common technique is the so-called radial velocity. And what this is again, you're looking at a solar system that's kind of edge-on, like what Kepler's looking for, but you're looking for the gravitational effect of the planet on the star. And so as the planet orbits the star, it tugs on the star slightly, and you can measure that velocity shift. And by carefully measuring that velocity shift, you can find the planet. And so this has been the most common technique. And what this plot shows is it shows all the planets that have been found based on the period of their orbits. And this is a logarithmic plot. So this is 1 day, this is 10 days, 100 days, 1,000 days, and so forth. And up on the vertical axis is the mass of the planet. And so there are a number of ways to infer the mass, but this here, 1, is the mass of the Earth, and then a Neptune-sized planet would be right about here, and then the Jupiter ones, Jupiter is about 318 times the mass of the Earth. So you can see that there are lots of massive planets that have been found, especially through this radial velocity technique, because it's easier to measure the velocity of a star when you have a big planet orbiting it. The star has a bigger kick due to the planet. So these are all the planets that have been found not by Kepler. And here's what Kepler has found as of last year. And right now, I think the current numbers are, we have about current meaning today, in 2015, we have over 2,000 planets that are known outside the solar system, and about half of them, so more than 1,000, have been found by Kepler. And what this is showing, I think is also really interesting, is that Kepler allows you to find planets that are smaller than Neptune and Jupiter, although it's finding lots of Neptune-sized worlds. But you can see these other techniques tend to find Jupiter and larger sized planets, but Kepler is good at finding worlds that are smaller or about the same size as the Earth. And in fact, just recently, they announced a discovery of a Mars-sized world. So you're seeing worlds that are smaller than the Earth, and you're also seeing finding worlds that are orbiting out to in orbits that are where we would think the Earth is orbiting. So the Earth would be right about here in this plot if you were to plot it. All right, so Kepler has had a lot of success, obviously, and it's one of its main goals, as I said, is to look for Earth-like planets around Sun-like stars that are habitable. And so here is just an example of some of the worlds that it's found. And we have the Earth and the Sun, and the stars are not to scale to the planets, obviously, but the stars are to scale to each other. So these stars are all correct relative to each other, and the planets are also scaled to each other. So in 2011, there was an announcement of Kepler 20e, which is a world just slightly smaller than our Earth. So this is the closest world that's in size to the Earth that was found, but it was orbiting about 5% of the distance between us and the Sun. So it's thought that the surface is probably over 1,000 degrees. So there's no way that liquid water could exist on its surface. But at the same time, they also announced the discovery of Kepler 22b around a different sun. And here was a world that was twice the size of the Earth. So this is definitely one of those super Earths. And it's also orbiting in the habitable zone, which makes it really exciting. But because this is such a different world, being twice as big as our Earth, we can't say very much about what the possibilities of life are, but that's really exciting. And last year, there was an announcement of Kepler 186f, and this was a world that was just slightly larger, about 10% larger than planet Earth, but it orbited a what's known as a K dwarf, meaning a star that's smaller and redder than our Earth. So that, again, is not very much like our solar system, but this particular world is also in orbit around its habitable zone. So that brings up interesting questions about the possibilities of life on that planet. And then finally, this month we had the discovery of Kepler 452b, which as I said, is about 60% larger than the Earth. And the star that it orbits is very similar to our sun. This particular star is only about 10% brighter than our sun. And so this is the paper, Discovery and Validation of Kepler 452b, a large, or a 1.6 radius Earth, super-Earth exoplanet in the habitable zone of a G2 star. And the primary author is John Jenkins, who is at NASA Ames. And here is the transit data. So this is like that plot, that animation that we saw, but this is actually from the paper. And so this is actually all of their data sort of folded together from almost 4 years of observations. And the transit took about 10.5 hours. So you can imagine they had to have computer software going through literally 4 years of data to be able to parse out this transit data that for a transit that lasts only about 10.5 hours. And the individual points are the actual data, and then these bigger blue circles are where they bin the data together to give you, because as you can see, the individual points are pretty noisy. And here is how the 452b system looks compared to our solar system. So our solar system is down here at the bottom with Mercury, Venus, Earth, and Mars. And here's the 452 system. So very similar star, except it's slightly brighter. And so what that means is this green region represents the habitable zone. And so the habitable zone is slightly further out as a result of the star being brighter. But you can see that 452b orbits right in the middle of, or right in the habitable zone. And it only orbits about 5%, I think about 5% further from the sun than the Earth does. So in many respects, it's very similar to our Earth orbiting our sun. Its year is about 384 days as opposed to 365 days for the Earth going around the sun. And then also shown in this graphic is the 186 system. So I said earlier, this is the one that is a K dwarf, meaning it's a much dimmer, redder star. And because it's dimmer, the habitable zone is also much smaller because the planet has to orbit closer for it to be neither too hot nor too cold. And what's really interesting is that you can see that this planet, even though it's in the habitable zone of this particular system, it's basically at the same distance as Mercury in our solar system. So this gives you a sense of how diverse potential solar systems can be throughout our galaxy. Not only can you have solar systems with habitable planets in sun-like stars, but potentially dimmer stars, and also potentially much more massive or brighter stars, although We don't really have too many examples of those. All right, so you might have noticed that one term that I've used is planetary candidate, and that's because even though we see these transits, astronomers still have to confirm that a planet is actually there. And it turns out that there are lots of ways in which you can have a false positive, meaning the signal looks real, but there might be other things involved that can fake a transit signal. And so even though Kepler gives you this initial indication that a planet is there, you still have to go and get additional observations to nail it down, to really say that there is a planet. And so one way you can do it is to go and make those radial velocity measurements, trying to measure the reflex motion on the star due to the planet. And in this case, they really couldn't do it because the star is too far away, 1,400 light years. And the planet is too small, meaning the effect of an Earth-sized planet on a sun-like world, that motion is just too small for us to measure. So that was not possible. But what you can do is there are other tests and other observations that you can make, and then you can then make statistical arguments to then argue that all of the other scenarios that can cause a planet transit-like event, those are far, far less possible or statistically than having actually observed a planet. And so in this case, you basically rule out a lot of other scenarios. And so one possibility is that there might be another star that is in the same direction as the star that you're trying to observe. And perhaps instead of the transit occurring on your target star, maybe it's a transit occurring or something else that's happening in that background star. So perhaps one possibility is you actually have a binary star, and you can have binary stars that are so close together that they can actually mimic a transit occurring. And so there are a number of things that you can do to rule out an eclipsing binary. But one of the things that they did was to actually go and observe this particular star with the Keck telescope, and to actually look for any signs of background stars. And so they weren't able to find any. This is the same Kepler 452 star in the near infrared and under two different filters. And you might see all these weird little speckles or dots around. You can see these little fuzzy dots, and those are actually just artifacts from the telescope. But it's pretty clear that there's no background object. But they went and used observations like this, as well as other observations and other types of tests to basically rule out not only eclipsing binaries, but foreground or background stars that happen to be transited by a planet, and also even the possibility that this is not a single star, but a double star or a triple star. And it's the companion of the other star that's being transited by a planet. So, with this confirmation, now we can make a plot like this, where they basically show all the worlds that have been discovered by Kepler now, which number about a dozen, which are in orbit around or in orbit in the habitable zone of their star. So what this plot is showing is that this is the amount of energy being received by the planet from the starlight that's falling on it, and scaled in such a way that Earth is exactly 1. So this is twice the Earth's energy received, and then this is a tenth of it, so that's 0.2, 0.3, 0.4, and so forth. And then this is the temperature of the star, and this gives you a sense of how massive and how bright it is. So our sun has a temperature about 6,000 degrees Kelvin. But what you see is that all of the previous discoveries of planets in habitable zones have been with redder and dimmer stars. And then these planet circles are also scaled to the size of the world. So you can see that 452b is blinking. It's about 60% bigger than the Earth, but many of these other worlds are larger. They're definitely in the super Earth category. This one is almost about the same size as the Earth, but you can see it's also right at the edge of the habitable zone. All right. Another thing that's really interesting is that, as I mentioned earlier, 452, based on our stellar models, is about 6 billion years old. So it's about 1.5 billion years older than our solar system. And one thing that happens to stars, to all stars, not just to our sun, but they actually get brighter and slightly larger with time. And so even though these our sun and Kepler 452 are very similar, because 452 is 1.5 billion years older. That means it's putting out more energy than it was earlier. And so what this chart shows, and we'll actually see this in animation, is basically how the amount of energy that has been received by the Earth and 452b has changed over the lifetime of the two solar systems. So currently, the Earth is here, 452b is here, but if you look, 3.5 billion years ago, the Earth would have been back here, and 452b would have been back here somewhere. But in all these cases, basically throughout the history of both solar systems, both planets have been in the habitable zones of their stars. But you can see that eventually, far into the future, so given another 4 billion years, 3 billion years for 452b, and another 4.5, 5 billion years for our Earth, this, both the suns will get bright enough and hot enough that these planets, both our worlds, will slip out of the habitable zone. And so this animation shows how the planets evolve as far as being within the habitable zone. And there are different limits to habitability that have been calculated by theorists, and so these show two different ones. So what this says is that both our planet Earth and 452b have, up until now, always been within their habitable zones, and so 452b has had 6 billion years if it has a rocky surface and if it has liquid water, a huge amount of time for life to possibly evolve. So once we have telescopes that can sense the tracers of life in alien atmospheres, 452b would be one potential candidate if they were able to, the telescope was powerful enough to look at something that far away. All right, here again is another diagram showing all of the worlds that have been known, that have been discovered, that are in the habitable zones of their parent stars, and again, breaking it down to the dimmer K stars and the M stars, and here is 452b with the G stars, like our sun. And what this plot shows all of the planetary candidates that are currently known from the Kepler survey. And the Kepler team releases catalogs of all their discoveries periodically, meaning they release basically tables showing all the stars that have potential candidates. And so these blue points are the candidates from January of this year. And for the 7th data release, which came this month, they added about 500 new planetary candidates. So now the number is at just under 4,700. And again, this shows you that there are plenty of candidates waiting to be confirmed that are Earth-size, and ones that are potentially at the orbiting at the same distance as the Earth. So you can see a bunch here clustered that are blue that haven't quite been confirmed yet, as well as a few new ones that have been added in this data release. And this is yet another plot showing the the candidate planets, including ones that are confirmed. These are the ones that are filled in. So those are the dozen that we've been talking about. And then a lot of these open circles are ones that have yet to be confirmed. So again, there are lots of candidates that are potentially Earth size, if not almost exactly the same size of the Earth, maybe slightly larger, like this one and this one, that are orbiting a G-type star. So what this diagram means is that we will undoubtedly hear more about exciting new Kepler news about Earth-like worlds in the coming year or two as they look through these candidates and try to confirm them. And then finally, one other interesting thing about this particular data release is that it's been very difficult for the Kepler science team to keep up with the potential planetary candidates, just because there's a lot of manual work, meaning someone has to go through and examine the data manually. And so what this shows is Kepler objects of interest. That's what KOI means. But over the years, it's shown that the ones that are have actually been examined are the ones in blue, but the ones that haven't been examined by a human are the ones in gray. And so the number of candidates has grown so much that they just haven't been able to keep up with the potential discoveries. But just recently, they've managed to automate, meaning write computer algorithms to do some of the grunt work that the people had to do. And so this really sped up the whole process. And so now, the number of candidates is still about 4,700, but they've been able to rule out all these other objects that had been waiting in the queue. So with that, I'm going to end my story. But what I wanted to point out is that it's really only been 20 years since the first major extrasolar planet discovery in 1995. 51 Pegasus B was announced by Didier and Mayor, and so it's and so 51 Peg is one of these giant Jupiter, actually much larger than Jupiter worlds that orbit really close to its parent star. And the reason that they were able to find it is because this world is so gigantic, and the reflex motion on the star was also very visible. But we've progressed quite a bit in our technology and in our techniques, refining those techniques so that we've gone from super Jovian worlds to basically Earth-sized worlds that are very similar to the Sun-Earth system. So that, I think, is quite a bit of progress in a relatively short time.